Hello and welcome to this video tutorial for ANSYS Mechanical. The content of this tutorial is buckling analysis. So on the screen now, if we animate these results, I have just completed a buckling analysis of a slender column under a compressive load, and the results show the buckling mode shape and load multipliers. So before we get into the details of how I went through this workflow, I'll close ANSYS Mechanical. And if we have a look at Workbench, the key here is in the setup. So as per normal, we have our geometry from Creo. We've then sent that into a static structural solve, and the solution of our solver has become the input for the eigenvalue buckling analysis. So the resulting stiffness matrix has been used as input to deduce buckling factors. So we'll close this and have a look at what we've got in Creo. So I've built a very simple surface model of a bit of angle column. So this is a surface feature. It has no thickness. It's approximately 2 meters high and 100 mil in width. So I've just built that as one extrude. I'll then push that into Workbench. Okay. Now I'll start by dropping and dragging the static structural solver over the geometry. So that column has now been linked. But before we do any meshing or solving, I'm going to take the buckling tool here and drop that over the solution. So the solution from the static structural will be used as inputs to determine buckling factors. So I'll drop and drag that over the solution. And you can see how that's used as input into the setup. Okay, now that we've got our workbench set up, I'll double click on the model and launch ANSYS Mechanical. Okay, so we have our surface geometry. Now this will be represented as a plate mesh. Now the utility of this is it allows us to change the wall thickness very easily rather than having to remodel the whole feature. If you also notice, under the static structural toolbox is the buckling analysis. So there is a bit more setup to be done before we can get the results. Okay, but there's a question mark here, and it's highlighted it wants a thickness. So this is the real benefit for using surface models in Creo, is we can then update the thickness later. So we might make this 5 millimeters. The material structural steel. And if we realize our design isn't valid, we can then change this to 6 mil or 7 mil or 10 mil, for example. So we can do some quick prototyping with this surface model. So we have a tick here. Our mesh, under sizing, I want uniform, because visually it's a uniform engineering section. There's no complex geometry to take care of. And I'll set the minimum size and face size to 10 millimeters. Oops. And that should give us uniform square elements. So we'll generate this mesh. Okay, it's a bit hard to see, but if we zoom in, we've got our uniform square elements. Okay, we have a tick with our mesh, so we're happy there. Under our static structural solve, we'll add some support. So this is a column. So I'm going to fix the bottom edge here, holding down Control. So this is a fixed connection. I'll zoom out. I'll add a load to the top. Now this is a column under compression. So I'll select the top surface. Now the thing to note here is under the loads, I'm going to apply a load of -1 Newton in the Y direction. So the reason I'm doing that is the resulting load multiplier or buckling factor from the buckling analysis will be equal to the force required to cause that to buckle. So if we don't know our initial design load, just set it to -1, and then you can look at the safety limit in buckling later. If we have our given design load, we can put that in. Okay, so there we go, very simple column. I've just meshed it quickly, fixed the bottom, and applied a load of 1 Newton in the negative Y direction. Okay, in the eigenvalue buckling analysis, the setup here is quite simple. We might find the maximum 4 modes. Typically the first mode is of most significance, but I like to include a few more just as a bit of a common sense check. And we want to include negative load multipliers. Okay, so if I right click on that, it's going to solve the static structural, use that as input, and then solve for eigenvalues. So this might take a little bit longer, but that mostly depends on your mesh. Okay, so that's completed, it's ticked. We'll have a look at our messages. So there's no warnings or errors, which is good. If we have a look at the solution, we can see our first four load multipliers. So typically the first one is of the most significance because it's going to buckle at 1,886 newtons. This is more of a common sense check. Okay, we can visualize this. So if I insert the deformation, total deformation, and I evaluate that, it's a little bit difficult to see, so I'll change the mesh to undeformed wireframe. So the wireframe is the initial model, and the deformed one at the displacement scale is the shape the column will take at the onset of buckling. As this column continues to buckle and undergoes plastic deformation, that's quite a complex piece of phenomena to model. So at the onset of buckling, we can see what's going to occur, and it's relatively intuitive due to the fact this has been clamped at the bottom and a load has been applied here. So the main conclusions from this is that at a load of 1,890 newtons, this column will buckle, and at the initial onset of buckling will take this shape. We can then animate that by pressing the play button. And if we expand our menu, we get a graphical representation of our first 4 modes the load multipliers, and the value on the bar graph. We could also click the second mode, right click that, retrieve this model. So this is the second mode. Once again, fairly irrelevant because it's not going to achieve this without passing by the first mode, but it can be a useful sanity check. Okay, so that wraps up a quick introduction to buckling. The key things to note is in Workbench, you link the geometry to the static structural, and then the solution to the input for eigenvalue buckling. The setup is virtually the same. You include your plate thickness, you mesh your model, fix it appropriately, and I like to apply a load of 1 Newton for the buckling factor. And once you've done that, you can execute the buckling solve and view the results.